So yeah, my name is Vincent. I'm a research advocate here at Rasa. So I do a little bit of research, do also a lot of explaining in the DevRel team. And what I want to do today is just talk about these benchmarks. And I'm sure you've had this experience where you look at this academic paper and there's a table in it. There's a whole bunch of methods and things that they've tried. And there's this one little number that's like in thick, bold black. And that number is telling you, well, that number is referring to a model and that model is the best one. And a lot of effort is spent getting that one number as high as possible. And I get it. It's a benchmark and you want to sort of optimize grid search and whatnot. But what I've started noticing is that there's also a danger because that whole grid search benchmarking part can be quite distracting because at some point the benchmark might no longer reflect reality. What I would like to do in this talk is just demonstrate some tools that I use whenever I do benchmarks. But moreover, what I hope to do is also show you not just the tools, but also the methodology and the way of thinking. What I'm going to do is I'm going to do an intent classification benchmark. I'll show you some of the results, and we're going to see some fishy details. Before diving into that, what I do want to point out is that I will be using this tool called What Lies, and there's a reason why we're going to be talking about this tool in a bit. What Lies is a package that I made on behalf of the research team a while ago, and it's basically this scikit-learn compatible visualization tool for word embeddings. I noticed a while ago that word embeddings, although they're great, if you're using word embeddings from Spacy, the API is completely different than if you're using TensorFlow Hub or Hugging Face. So I just made this one little package. It just makes it easy for me to say, look, if I have text, I just want to use Spacy or whatever backend is available to me, and I want to use the same API to get this vector or this word embedding out. What Lies comes with a bunch of visualization tools that are great because I like to use these tools to do a little bit of analysis on bias in word embeddings. But for the purposes of this talk, there's also this one other feature that's really nice, and that is the fact that this tool is also scikit-learn compatible. Here's a language model. This is the byte pair language model. It outputs vectors, and the whole point of this is that byte pair models exist in English, but they exist in 275 languages. But what I can just go ahead and do is I can say, look, I just want to have these English embeddings in my scikit-learn pipeline. And if you're familiar with scikit-learn, it's as if you're using a count vectorizer. You just have your scikit-learn pipeline over here. And effectively what this will do is this is going to make sure that words can come in and vectors are going to go to your logistic regression. So if you're just interested in, hey, are these word embeddings going to be useful for my specific use case? You can still just use scikit-learn. And you can just try out a whole suite of these embedding models, also for lots of different languages. I also use this tool to explore non-English language tools, so to say. So this is great. Like I can very easily pluck any CSV file from Kaggle to sort of do any sorts of benchmarks with this, and that's something that I'm going to be doing in a moment. And the main thing that I'll be interested in is if I put like a heavyweight BERT kind of model in here, what's the performance going to be? And what's going to happen if I put maybe a lightweight model in here? Is there going to be a bit of a difference? It's kind of the benchmark that I'm interested in running. But okay, this is the pitch of What Lies. This is the main tool that I'll be using. But let's now actually run the benchmark. And now I'm not going to run the benchmark live here, of course, because it takes a while. But just to get an impression of the task that we'll be trying to solve is I have gotten this intent classification data set. It's from Clink. It's straightforward intent classification in the sense that, I've got some text over here, and I would like to map that text to an intent. And if memory serves, this data set has about 150 intents, and each intent has about 150 examples in it, except for one intent, which is the out-of-scope intent. And if memory serves, I think that has 3,000 examples or something like that. But in total, this is a data set that's actually kind of big. It represents something. It's like 20,000 or plus data examples. And what I'm going to do is I'm basically going to be running this pipeline. So I'm going to be saying, look, I got some text going in. I'm going to give that to some embedding from What Lies. In particular, I'm going to give it fast text and the universal sentence encoder, the BERT variant of the universal sentence encoder. And I'm going to get my dense representation out. I'm also going to be doing the count vectorizer trick with the n-grams, so I get like all these subwords in a sparse representation. But effectively, both of this is going to go to my logistic regression. I'm just going to see what performs best. That's the task that I'll be running. Oh, Let's do a couple things then, because you can imagine that this is going to result in a table. I'm going to get this table that says universal sentence encoder, some number, and fast text, and then some other number. But if I'm going to be doing a proper benchmark, then I might as well also just add the simplest possible thing to the mix. What I should also be doing is I should maybe also say, well, let's forget about the embedding at all. Let's also just only do the count factorizer thing, because that's the most simple benchmark that we can get. And obviously, all the other models should outperform that by a large margin. If I don't include this, then I will argue that my benchmark actually isn't that fair, and it's something that I don't see every paper do. Every proper benchmark should have the simplest possible algorithm amongst them, because otherwise it's just really hard to make a proper comparison. But for this audience, I would also like to propose we go even a step further, because there's an extra cool thing that we can do. Notice that we actually have quite a bit of data examples here, right? So I can do my train test split thing, but I can also say, well, maybe I'm not just interested in the effect of the embedding. Maybe I'm also interested in the effect of the size of my training data set. And what I'm about to show you is just this tool that I like to use to visualize a large grid and to play with that. This is a tool called HighPlot, and what we're looking at here is a parallel coordinates chart. What it allows me to do is it allows me to compare the embedding, the train size that I've used, the accuracy on my test set, the accuracy on my train set, the prediction time, and the time taken for training. What I can do is I can just say, well, what happens if I take all the runs where the time taken was very long? Okay, these were the examples with a large train size, and they were all from the universal sentence encoder. And this HighPlot tool just allows me to make a quick selection, which is very, very useful. It also allows me to indicate a color. So I can say, well, the accuracy on my test set here, well, that's the main thing I would like the color to be. And that makes it easier for me to compare. Now, one thing that's interesting here is I can say, well, let's select the instances where I don't have a whole lot of training data. And let's move that up. And in particular, pay attention to what happens here. As I increase my train size, it seems that the accuracy in my test performance actually goes up quite a bit, and the accuracy in my train set actually goes down a bit. The tool is called HighPlot, by the way. I see people asking that. But hang on, if I look at it this way, then you can also sort of say, let's look at the top performing ones, and let's just see what the pattern is. And if I look at this, then it seems like the highest test set performance isn't necessarily correlating with any of these embeddings. No, it's just correlating with a super large training set size. Okay, so this is a clue that tells us a slightly different story, and it's going to become even more obvious when this is a tool called Altair. There's an interactive visualization that I'm making. But let's now actually look at the chart, what it looks like if I have my train size on the x-axis over here, and if I just look at the accuracy number, how that's going up as my train size increases. And well, I hope you agree. When you look at it this way, I mean, let's zoom in a bit, because there is a difference between the universal sentence encoder and fast text and the n-grams, right? But this difference, I don't know, is maybe 1%. And the funny thing, if you want to see the difference between fast text and just count vectors, I mean, it's an order of magnitude 10 to the power of -5 or something like that. It's really, really slim to none of a difference. But okay, I guess we could say that the universal sentence encoder is the best performing one. But if you see a table with just that number, then you're missing out on probably what is the most important point. And that is the fact that if you want to get a better model, you shouldn't be playing around with a fancier embedding. You should just maybe add more data. You can have a look at maybe we have to zoom in just a little bit more. But if I consider this, I would say, well, there's still definitely a bit of a slope. If I increase the data set more, then, more accuracy. And to really zoom in on this embedding part, it's just going to be a little bit distracting. And I get it. If you're trying to make an academic article or a good blog post, you have to make some number with some sort of comparison. But I hope you do acknowledge that that accuracy number is just a single number. It's a huge dimensionality reduction of stuff that we're actually interested in. And if I'm speaking about stuff that I'm actually interested in, let's look at the data set one more time. This data set contains a couple of intents. There's the out of scope one that I've mentioned earlier, But let's look at a couple of other ones. Apparently, in this data set, you can play music. There's a to-do list. You can ask for a travel suggestion. You can ask for a calendar update. You can ask for a name. You can set an alarm. You can ask for a new card or your balance. When you look at all these different intents, you also come to the slight conclusion that it seems to be a smorgasbord of all sorts of intents that could be inside of a virtual assistant. But I'm having a bit of trouble coming up with a single virtual assistant that I've ever interacted with that actually has all of these intents implemented. And with that kind of comes to the conclusion that this data set doesn't represent reality. For starters, because the intents don't match an actual existing assistant. Another problem is that because all of these intents are so separate from each other in terms of words that are being used, you're typically just going to get these clusters of words that don't overlap at all, which is different if you're using a banking app. I mean, words overlap there all the time. But what's worse is also that this data set is really only about intent prediction. It's not about action prediction, which is the harder part of making a virtual assistant. And what I'm hoping to sort of get into your mind here is that maybe we need to take these benchmarks with more grains of salt than we currently do. Maybe if we want to improve the model, the story is a little bit more surrounding the data than maybe the algorithms that we're applying it on. And with that in mind, there's actually like another story that I would like to share about this topic. Because we're not just dealing with benchmarks these days, we're definitely also dealing with pre-trained models that come with benchmarks. So very often you might get this model card where people are convincing you that, hey, we have this pre-trained model and it's great. You can go ahead and use it. Here's the accuracy number. But also there, I would recommend people to be extremely careful. And the best example of this phenomenon is in toxic language detection models. Now, toxic language detection is actually a very noble cause, and like we should totally research that, and we should make models for it. All that stuff's great. But let's do a quick experiment. I used the toxic language detection data set that's on Kaggle. It's the first challenge that was shared there. It's from Google, I think. And it's an imbalanced data set. There's a lot of texts that are fine, but a couple of these texts are just toxic. You could argue this is text that if I saw it on a forum, I might want to ban a user. It's that kind of thing that I want to detect here. So, okay, what I can do is I can make a machine learning pipeline, and I'll spare you with the boring parts of the benchmark. But it turns out that the count vectorizer model is actually among the top 3 of the models that I tried. And, I get like a 94% accuracy. And on the toxic text, I have a precision of 75%, which, isn't bad. Let's, for all intents and purposes, assume this is a somewhat reliable model and these numbers that they're likable. They're not necessarily perfect, but let's say this. Then there's still a huge problem, especially with toxicity detection. And the only way you're going to figure this out is not necessarily by looking at the number, but by just interacting with this model and to just qualitatively see if you can poke a hole in it. If I give the model the text, I like the conversation, then it's fine, not toxic. Okay, good. If I give it the text, I do not like this conversation, that's fine. Again, okay, correct. You are cool, that's fine. But if I were to say, dude, that's totally badass, well, let's remove this predict part here, but we have to rerun this. Live demos. There we go. If I say the sentence, dude, that's totally badass, it gets predicted as toxic. Now, it makes sense because the word bad is in it and the word ass is in it. But I also hope that you acknowledge that if, 16-year-old Vincent is telling this to a buddy of his, then maybe it's slang, but it's by no means a toxic comment. In fact, you could argue here that whether or not this is appropriate behavior, that is very culturally dependent. My mom and dad might think it's poor taste, but teenager Vincent would argue it's completely fine. And this is also an issue with a lot of these benchmarks. They're usually relying on this data set that comes with labels that have to assume it's true. And in this case, it's a fairly innocent example because it's, slang and it's about teenagers. But if you're interested in this topic, definitely give this paper a read. There's a paper called The Risk of Racial Bias in Hate Speech Detection, where they actually demonstrate that a lot of these hate speech detection algorithms, because they're labeled in a particular way, they're not immune to cultural bias. And that's actually a huge problem. And the only way you're going to be able to sort of not necessarily mitigate. No, so the main thing I would like to leave people with is there's also another example where labels can be biased. There's a paper that I'll share is apparently there's like label mistakes in MNIST as well, like the very common digit detection data set. Like that data set has issues in its test data as well, which means that a lot of the benchmark numbers that you see on that data set might just be off simply because the labels are off. The main thing that I'm hoping that I got across during this talk, though, is that, take benchmarks with a grain of salt. There's probably more important things that you could do, especially in the realm of just iterate on your data instead. Probably it makes more sense to understand your problem a bit better than that you're going to worry about, state of the art or that sort of thing. Please understand your problem and focus in on that, because if you're doing that, you're already doing plenty.